All right, so we're going to wrap up section 13.1 by doing some more examples, but we're not going to sketch any of these. We're just going to quickly describe them based upon kind of identifying what the traces are in our heads or using the equations that are given on pages 821 and 823 in the textbook. So instead of sketching all the traces, we're going to try to do this a little bit, use a little bit faster approach to describe these. So we're on page 823. We're going to start with number 42, which is z equals x squared plus y squared over 9. Z equals x squared and then plus y squared over 9. So now, if I put in y equals 0, I get z equals x squared, so I get a parabola. If I put in x equals 0, I get z equals y squared over 9, which is also a parabola. So I'm getting these parabolas that open up when I look in both of those. Now, if I said z equal to something, whatever z equals 1, in that case, I get an ellipse. So if I look down at this thing, I would have an ellipse. So parabolas open up in the x and the yz plane, and the xz plane. And then ellipses when you look down, so this thing will be an elliptic paraboloid. But you also can just use the equations on pages 821 through 823. And this will be opening in which direction? Up, down, left, right. Which way would that open? So one thing to keep in mind when you use those equations on pages 821 and 823 is that don't get hung up on the placement of the variables. Even if, say for instance, I had this x equals z squared plus y squared over 9, that still is an elliptic parabola. The only thing that's going to change is this unofficial part, this which way it opens. But if you just ask for what it is by name, that would be it. But oftentimes you want to know which way that thing, quote unquote, opens or what axis it runs along. So let's look at next number 44. Number 44, we have z squared equals x squared plus 4y squared. Z squared equals x squared plus 4y squared. So here, if I plug in, say for instance, z equals 1, I would get an ellipse. So I could see that it would look like ellipses. Or if I put in z equals -1, I also would get an ellipse. So I can see that there are ellipses there. If I do x equals 0, I'm going to get a line. If I do, or 2 lines. If I get y equals 0, I will get 2 lines as well. So that gives me an idea. When I look from above or below, it looks like ellipses. When I look from anywhere around it, it looks like a cross. So this thing would be a double cone. So this is an elliptic double cone. And remember, you don't have to go through that traces rationale that I was going through. You can just use the equations that are in your book. Now, along what axis? So this will be along which axis? So see if you can figure that out. 46. Y equals 1 minus x squared. So y equals 1 minus x squared. I don't see any z's, so that means z takes on every value. And just for the sake of time, I'm just going to say z is free. All right, so this thing right here, if z were 0, this would be a parabola. So now when z takes on every value, that makes this a parabolic sheet. So this is a parabolic sheet. And if you go through and identify stuff this way, then you can look at the picture in the textbook and sketch based upon that picture. The only thing you would have to change is this part where I'm putting the question mark. So you might have to change which direction it opens or which axis is along. So this is a parabolic sheet along what axis, opening which direction, up, down, left, right, forward, backwards. 48. 48, they give us z equals y squared minus 4x squared. Z equals y squared minus 4x squared. Okay, so here if x is 0, I get a parabola. If y is 0, I get a parabola. So when if I looked at it from the front or from the left or the right or the back, I'm going to get a parabola. So now what if, say for instance, z was set equal to something? If I set z equal to 1, then I would get a hyperbola. So when I set z equal to some non-zero value, I get a hyperbola. So that means when I look at it from, say for instance, with z equals 1, if I were to look at that thing from above, then it's going to look like a hyperbola in that scenario. So this is going to be a hyperbolic paraboloid. Because it's made of hyperboloids and parabolas. When we plug in and we look at our traces. Then 50, let's look at that one. 50 is y squared minus x squared equals 4. Y squared minus x squared equals 4. So notice a variable doesn't show up here. Z doesn't show up, so Z takes on every value, or we'll just call it free for now. So Z takes on every value. Now, what does this thing look like for, say, Z equals 0? We have a difference of squares equals some constant, which means this thing is going to be a hyperbola for Z equals 0. And then we're going to take that hyperbola and we're going to just drag it along the Z axis. So here you're going to get 2 hyperbolic sheets is what this is called. So 2 hyperbolic sheets. And then we'll do 52. 52 is z squared plus 4y squared. Z squared plus 4y squared minus 2x squared equals 1. Minus 2x squared equals 1. All right, so if I had z were 0, then this thing right here is going to be a hyperbola, excuse me. If I had y equals 0, I would get a hyperbola as well. And if I had x equals 0, I would get an ellipse. So you would look at, okay, well, z equals 0. So if I look from above or below, then I get a hyperbola. Y equals 0. When I look from, your y is 0, so when you look from the left or from the right, then you're going to get, and this is left and right, given the way we set up our coordinate axes, you're going to get a hyperbola. But when I look from, when you do x equals 0, then you're going to get ellipses. So x equals 0, you look from the front or the back, it's going to look like ellipses. So this is going to be a hyperboloid of 1 sheet. Hyperboloid of 1 sheet along which axis would you say that would be along? All right, so we'll stop section 13.1 there, and then in our next video we'll start section 13.3. 13.2 we're going to skip, and so 13.3 will be the next section that we cover.